All right. So the slides here, they just show how to make the selection. There is an explanation. We already went through that. So I'm going to skip all these slides and go to more examples for deriving the material indices. Okay. So let's derive material indices with strength as the parameter. Okay. Go here and design. Okay. I think this is the one we finished last time. So this should be lecture 7 or lecture 8. Okay. 8 and section 1. Okay. All right. So let's go to this problem again, axial load problem. With, okay, still not working. Just 1 second. Okay. Okay, so again, just like the previous case, we assume an axial load problem. The load P, except we are going to get the objective. The objective is going to be slightly different. Let's see here. Where is the problem? Here. Specific strength. Yes, we have the strength. Okay, so I'm going to give the objective for this problem. Design, find the material indices such that you get a light-weighted, strong beam. Instead of stiff beam, a light-weighted, strong rod, not a beam, it's a rod. Okay, so since it is a rod, okay, so as usual, objective function. What is the objective function for this? Can one of you tell me? What is the objective function? I have given here light, strong rod. So what is the objective function?
Minimize mass.
Minimize mass, yes. Minimize mass, m, and as usual, we express it in this form. Now let's give some fixed variables. The rod length is fixed. Any other dimension we can think about? P is given. And that's about it. Okay, so we have fixed variables. Let's underline this. So what are the fixed variables? We have L and P. What are the free variables? What could be the free variables? Any density? Yes. Then
area.
what else? What else we have? Area of cross section. Yes. Shape of the cross section. These are free variables. Okay. So leaving this, now what is our aim? What other quantities are given? We are given strong rod. So something about the strength is given. So let's assume Here we are given yield strength, for example. Okay, so yes, y asterisk. So this is the strength parameter we are given. So we have to also input strength parameter here as the fixed or minimum value. Okay, so greater than should be equal to this value. Okay, so how do I write an equation? Assuming Hooke's law is valid up till yield strength, we can write some expression for the strength. So what is the Hooke's law? We can see sigma is equal to E times epsilon. So from here, what we can do? We can rewrite it, and P over area of cross section is equal to E times change in length over original length. So I'm going to okay, so we want it in terms of strength, so we do not want to use this. Okay, so back it will go to the E values here, so we do not want to use that. What is the value we want to use? Rather, we want the strength parameters. So sigma is equal to P over A should be greater than or what do we say here? The stress developed in the material, okay, it should be always less than some strength parameter. So this we can say. So from here we can say, we can write A is equal to, take it to the other side and can write it as P over Sy. Okay, so we have an expression for A. Now we take the mass rho into A. A can be substituted y into length, and directly we get what is the strength parameter. What is the material index here? Sorry. So we can write P, the function separately. Then we have the geometry. Then finally we have rho over Sy for our case. So this is the material index, and we want to minimize this term. Usually we write the material index as the inverse capital M, okay, and then write it as Sy over rho, and we want to maximize this guy. Okay, so what is the chart we should use for this particular material index? It's very clear: yield strength versus density. So if you look at one of these charts, yield strength versus density, we can plot on the y-axis S and the rho value here, and S over rho is the line guideline we should select, and based upon the ratio of the values, we can see whether it is increasing or decreasing this ratio. Obviously the ratio is increasing in this direction and decreasing in the opposite direction. So let's try to see how it looks like in the software. So level 2. I'm going to draw the chart. On the y-axis, we want yield strength. So mechanical properties, select the yield strength. And on the x-axis, we want the general properties, and we are looking for density in particular. Click OK, and gives you this particular chart. So let's see if they are almost same. You can see same kind of charts, as except you are given this bigger bubble grouping all the foams together here. So in the same way, metals and other materials are also given here. We can draw the curve. We want to maximize S over rho, yield strength in megapascal, density, okay, and draw it. So let's see here. We can draw at various locations. Maybe if you try to draw the line over here, and this is the line you get, and it's same way we can draw more lines if you need. Okay, so you can draw these lines parallelly and make a selection. Now if you look here, if you want to get what is the slope here, value of the slope, yield strength over density. How will you get the value? You can get the value by pointing your cursor here to one of the points here. But in exams, what you will be given is a chart like this. Okay, so what we can do under those conditions, the value here is 1. Right at the 0 value, it is 1. Okay, and on the x-axis, the density values, absolute density values in kg per meter cube are given as 10 here, 100, 1000, 10,000. So the scaling here is on the logarithmic scaling. However, the values are absolute values of density. Okay, so here the density value rho will be equal to 10 at this point. At this point, rho will equal to 100. And you can see also some divisions here on the graph here. 1, 2, 3, 4, 5, 6, 7, 8, 9. If you include this one, 9 and 10. So there are about 10 points here. So the values will change as 10, 20, 30, 40, 50, 60, 70, 80, 90, and 100. Now between these, again we have 10 divisions. 100, 200, 300, 400, 500, 600, like that, 1000. And the next one will be 1000, 2000, etc. up till 10,000. Okay. So based upon the logarithmic scaling, the values are increasing 10, 100, 1000, 10,000, and then 100,000. Okay. In the same way, the logarithmic scale is given here, 0.01, 0.11 in multiples of 10. It's in logarithmic scaling. However, the values of the yield strength, they are given in megapascal. Okay, megapascal units. So it is 0.01 megapascal here, 0.1 mega, 1, 10, 100, and 1000 megapascals. Okay. What else can we say? Okay, again we have 10 divisions here, starting with what is the value here? So on the y-axis, this should be 0.001 here. Okay, and then 10 divisions here. So 0.002, 003 up till 0.01. And then from here to here, again we have 10 divisions. The values are 0.01, 02, 03, 04 up till 0.1. Again, we have from here 0.1, 0.2, 10 divisions. Okay, so now you know how to read this. We can get the slope by picking any 2 points. You can pick this point on this line. Okay, and then pick any other point, for example here, and get the corresponding values of the yield strength approximately. Okay, and then you will also have the density values, the 2 values. So based on that, we can easily get what is the slope. Okay, so in this case, let's say we have 2 points with the values rho 1, sy 1, and then rho 2, and then we have sy 2 values like this. It's easy to find the slope. Slope will be simply sy2 minus sy1 over rho 2 minus rho 1. That's it. Just find the slope in this way and you can get the values of the slope here. Okay, for this and this one. Now, you have to be careful about the units. Recall that the above value is in megapascal. Here on the denominator, we have kg per meter cube. So you have to get it in consistent units. Convert megapascal into pascals by multiplying 10 power 6. So that you will get correct values of the slope in correct units. So you have here Newton per meter square, kg per meter cube, and the final unit will be, if you reduce this, you are going to get here, so meter square, meter cube, we will get Newton meter per kg, or you can leave it as joules per kg. Okay, specific strength, or you can further expand it, kg meter per second square times meter over kg, and then you will get the result here, meter square meter per second the whole square. Okay, so that is the unit that you will have for this particular lines. So by calculating these values also, you will know in which direction the ratio is increasing, in which direction it is decreasing. But it is very easy to figure it out. When I am in this corner, the density values are very high, while the yield strength values are low. That means my ratio is going to be low here. And as I go up, the density, the yield strength value is high, but the density value decreases. That means the ratio is increasing. Okay. Okay. All right. So we have seen one more example. There are more graphs here. For example, let's say this is E versus rho. We have seen fracture toughness, for example, versus Young's modulus. There are other examples where you can have combination of fracture toughness and Young's modulus as the material index. And again, you can see the design guidelines, K square over E, K over E. Okay, so we will learn exactly what is fracture toughness later. Again, we have fracture toughness versus strength. We have thermal conductivity, not only mechanical properties. You can be asked regarding thermal properties as well. Mostly we will skip with respect to electrical resistivity, etc. Mostly only mechanical properties. Okay. Now, these are some examples I have solved. Let's go here and check more examples, what example problems here. So let's go here. Okay, it doesn't look like it is here. Okay. So I'm going to post more example problems. On material selection here. Okay, so let me see if I have posted chapter 2, class materials, lecture 2 here, and then okay. Okay, so if you open that, this one, okay, citation 2. Okay, so you will see more example problems being solved. You can go through the problems. So this is the example problem on strength for axial rod. We have already seen that. For deflection, stiff rod, there are more examples here for the beam case. Okay, in case you have you are asked regarding light stiff beam. In that case, how to solve for it, especially for a circular cross section. You are given here example problem for stiffness, light stiff beam. We already solved the problem. Again, you have here more example problems. So just go through these example problems. Okay. I will also post an example solution, okay, from last semester's exams. So let's see here. Turn one solution. I just want to check if I have the right material to be posted. Yes. Okay. So I'm going to post some of the one of the midterm examples here. Okay, so this is a simple example problem what I have. We will go through these questions later once we cover the chapters properly. But you can see here on how to derive material index for a slightly complicated case here. You have a diaphragm spring, and for this diaphragm spring you are given some formulas already here, and you are asked to derive what is the material index in this particular problem. The material index is derived here, and you can see the final form of the material index is in terms of the ultimate tensile strength over density square and E over rho square. So this is the material index. So this is slightly complicated, and you can go through this example problem. Again, we have, I think this is the diaphragm spring, and let's see here. This could be a leaf spring, sorry. So this is a leaf spring. Another example problem with the diaphragm spring. Go through this problem and try to understand how the material indices are derived and how we select materials. You are asked some questions again. If you go through these questions, you are asked select the material of the shaft using the Ashby's chart, and you are asked to give the reason why you selected a particular material, and again it is listed based upon what is the reason we select particular materials. Okay. So let's go here, go back to midterm solutions. I'm going to paste it right here, and let's put it in your system here. So the midterm will also give you an idea what kind of questions can be asked in this particular course. Okay, we can go through that. Okay, so we are done with this chapter on material selection, and we will move to a new chapter now. I'm going to close this. Let's go to the new chapter. Two, three, yes. Okay, so basically this chapter is going to be, we are going to recall completely what you learned in solid mechanics. I will not go through each and every slide, but I will give you specific topics which are to be covered and which will be useful in further chapters in mechanical design. Okay, so what are some of the specific topics we should be familiar with? You should know how to draw the free body diagram. Very important. Free body diagram. You should know how to draw the shear force and bending moment diagrams for beams in particular, because many problems we are going to solve by finding shear force and bending moment diagrams. And you will also learn what is called as Macaulay's method, using singularity function on how to draw the shear force and bending moment diagram in one go. Okay, you have to recall what is this concept of stress, especially in 3D, and you should know how to write the stress in Cartesian coordinate system. You should know how to figure out what are the principal stresses using Mohr circle or some other method in 2D and 3D. This is also extremely important when we go for failure theories, and you should know this. Okay, what else can we think about from you should know how to calculate stresses at various points in the case of beams or shafts, etc. So torsion, beams, etc. These are some of the problems. You should know when you have a distributed load how to calculate the stresses. Finally, stress concentration is also an important factor. You have to know how to calculate stress concentration. Now, additionally, there are other problems. For example, you may have curved beams. In case of curved beams, you should know how to calculate the stresses, but there are ready-made formulas for these stresses. You should know how to use them. Similarly, contact stresses can also be calculated. All right, so let's go to the chapter and let's see here. So this is a 3D case where you have a simple gear box. The gearbox consists of two gears mounted on two different shafts, and one shaft is an input shaft, another shaft is the output shaft. The gearbox is mounted on some maybe some kind of a support, rigid support, using bolts here. Now, if you are asked to draw the free body diagram for this particular case, for the gearbox, you draw it separately. Wherever you have the shafts here, at these points you will have bearings. The shafts are usually mounted on bearings. So on the bearings you will have forces on the plane of this plate over here, gearbox plate. So let's first identify the axis, X, Y, and Z axis. So on the Y and Z axis at points B, D, A, and C, you will have reaction forces. Since the gearbox itself is mounted using boards, again, you will have forces in 3 dimensions. Okay, so you will have 3 components here, 3, 3, 3. So this is how you will represent a free body diagram for a gearbox. For the shaft and the gears mounted, we can see gear G1 meshes with gear G2. That means between the gears there are forces. Okay, and the forces will be in a particular plane, and it's going to be on YZ plane. And we are going to assume these are spur gears, but if it is helical gear, then we will have forces in all 3 directions, so, along X, Y, and Z on the gears or between the gears. So we assume these are spur gears, and it leads to forces which is tangential to the contact point and normal to the contact point on the gears. So you can see radially normal force, and tangentially you have this force F. So if the forces on gear 1 or G1 are represented in this direction, on the other gear it will be in the same direction but opposite, same magnitude and parallelly in the opposite directions. Okay. Okay. So on the point B, for example, here you have the bearing and we have the reaction forces in particular direction. In opposite directions, we have the reaction force on the shaft here at point A, D, and C. So first thing in free body diagram is to recognize what are the unknown forces and what are the known forces. Mostly between the gears, the forces are known because we know what is the torque that is given on the shaft. Based upon the torque, we will be able to calculate what is the tangential force and finally the normal force, because we know the value of phi here. Phi is controlled by the geometric parameters. Pressure angle, phi is called pressure angle, and usually we get these geometric parameters from gear specifications. Okay. Okay, so the rest of the values are all unknowns except the torque and the forces acting on the gears, and we will be able to find out what are the unknown values of the forces by writing the equilibrium equations. So what is the final aim of free body diagram? To find the unknown forces, and by equilibrium of equations we find them, and once we find the forces, then we will be able to draw, for example, taking the shaft, considering it as a beam, we can draw the shear force and bending moment diagram and figure out what are the stresses. Using the torque, again, we can find the shear stresses, normal stresses, etc., and design the shaft. So that is the idea. So I'm not going to solve any problem here. We will go from 2D to 3D, one step at a time. Simple case, how do we draw shear force and bending moment diagram for a 2D, two-dimensional beam? If you have forces acting on a beam, okay, then you try to find what are the reaction forces R1, R2. Then you draw the free body diagram by taking several sections. For example, in this particular case, we need to make several sections like these, and then figure out in each section what is the internal moment and the internal shear force. And that's how we solve for each section and then draw the shear force and bending moment diagram. But before we do that, we should fix the sign convention. When we draw the shear force and bending moment diagrams, there are two sign conventions we should be aware of. Two sign conventions. What are the sign conventions? One for writing equilibrium equations. Okay, and the second one for drawing shear force and bending moment diagrams. So for writing equilibrium equations, we already know what is the sign convention. So let's go to the notepad here. So what is the sign convention we follow for writing equilibrium equations? On a 2D scale, this is the sign convention. We can extend it to 3D as well, or 1D as well. X is positive in this direction. Y is positive in this direction. Using the left-hand system, the right-hand system for the coordinates, we can see the rotation is positive in this direction. Counterclockwise is positive. Now, if you extend it to 3D, when you rotate it using your right hand rule, point the four fingers along this direction and extend your thumb. That will be the direction of your z-axis. which is perpendicular to the board, and it is coming out towards your face. So that is the positive direction for rotation. So using a right hand rule, you can figure out what is the positive direction for z-axis, and any rotation with respect to x-axis can also be figured out by finding the direction. For example, with respect to x-axis, this will be positive. Okay, and if you think about y-axis, positive direction is this one, in this way. Okay, so in 3D, for writing equilibrium equations, these are the positive directions for moments and for forces. Okay. This is the first sign convention. What about the second sign convention? For drawing your shear force and bending moment diagrams, you have a second sign convention. How do we get the second sign convention? This is the way you get it. Suppose you cut the beam on the right hand side. Make a cut on the right hand side. The shear force, internal shear force, will always be represented in the clockwise direction. It should lead to clockwise rotation of your beam. Okay, so that means shear force is going down. The bending moment should be such that it turns your beam into a vessel holding water from the top. Okay, so concave on the top. If you make a cut on the left hand side of the beam, then too your shear force must lead to clockwise rotation of the beam, which means my shear force must be pointing up in this case. And the bending moment, on the other hand, should again make my beam like in the shape of it can hold some water. Okay, so this is the positive sign convention for drawing your shear force and bending moment diagrams and representing the internal forces, internal shear force and internal bending moment. Stick to this sign convention as a standard, and stick to this sign convention as a standard. So these are the two sign conventions. We will see exactly how to use these sign conventions. So we have seen the sign convention. Okay, so your beam can have a distributed load, and if it has a distributed load, we will represent it as a function of x. It can be constant, linearly varying, maybe quadratic, cubic, or complicated like this. Okay. What is the relationship between the shear force, bending moment, and the distributed load? The differential relationship is given here. Shear force is dm over dx, and the load is dv over dx. And we can replace here dv with dm over dx, and then we get d square m over dx square. We can also express it in integral forms, and these integral forms can also be used to draw your shear force and bending moment diagrams. So if you know the distributed load, okay, then you can get the difference between any 2 points A and B. The difference in the shear force values will be given by the integral q dx between those points. In the same way, the difference in the bending moment values is obtained by integrating between those 2 points the shear force. Okay, just we are inverting this relationship what we are given here. That's about it. Okay. So let's consider a simple case here. Shear force bending moment diagram. Just to make you recall, these are very important with respect to solving all types of problems in design. So let's see here. You have the beam simply supported. We are going to assume it is simply supported R1, R2, and the length is about 20 inches. So in your exam, you will be given all problems in SI units and not in English units, that is not in inches but millimeters and meters, and forces will be in newtons, but here we are solving problems. Okay, so 200 and 100. We have 4 inches, a load of 200-pound force, and then 10 inches we have, what do we have here? 20. Okay, so it should be right on the midpoint. Sorry for that. Let's use a different color for forces. Force, and right in the center we have 100. Okay. Okay, so how do we solve? How do we draw the shear force and bending moment diagram? First, we need to figure out R1 and R2. Write the equilibrium equations. R1 plus R2 must be equal to 200 plus 100 equal to 300. Let's denote the points A, B, C, and D. Okay, so we don't have any point here, but that's what we write. And then we can take moment about A. What is the result we are going to get? Minus 200 times 4 minus 100 times 10 plus R2 times 20 must be equal to 0, and R2 we can solve. 800 here, 1000, 1800 divided by 20, so 180 over 290. So R2 we get 90-pound force. That's what we have here. And R1 will be 300 minus 90, 210 pound force. Now, so we have solved here. The next step is we take sections. We need to make a cut here, and cut here. Draw the free body diagram to figure out the internal reactions. So in the section AB, we draw the free body diagram. A. Okay, so that's the force R1. R1 we have already found 210. Okay. Since we made a cut on the right hand side, we use the second sign convention to represent the internal force, and the bending moment should be directed in this way using the second sign convention. We assume this is some arbitrary distance x on the section AB here. The distance is 4 inches, so that means my x varies from 0 to 4 inches. To draw the shear force and bending moment diagram, we write the equilibrium equation. What is the equilibrium equation for this? VAB, if I take sigma Fy, VAB is negative, and 210 is positive is equal to 0, which means VAB is 210 pound force. Write the same by taking moment about the right end here, okay, about this end, and we are going to use the sign convention for equilibrium equations. MAB is positive, VAB passes right through this point, does not contribute to any moment, and then we have 210, which is negative. It leads to 210 times x is equal to 0. So which gives me moment in section AB is 210x pound force inches. So in similar way, I'm not going to solve for each section. Similar way, we can draw from here all the way to this particular region here, BC. Okay, we can try one more. So section BC. Represent the free body diagram from point A all the way to point B, and then cross over, and before C make a cut. So at point A we have R1 equal to 210 pounds force. Then at point B we have 200 pound force acting down. Let's consider this A, consider this as B. And we know this distance is 4 inches. We are going to consider this distance as arbitrary distance x. Your x varies from what values? Take a look at it. From at point B 4 inches, from here to point C it is 10 inches. Okay, so between 4 and 10. Okay, that means your x values varies from 0 to 6. Inches. You can write the equilibrium equations as usual after representing your internal shear force and bending moment. We made a cut on the right hand side, use the second sign convention VBC and MBC for the section BC. Write the equilibrium equation. Sigma Fy gives you 210 positive minus 200 negative, and then minus VBC must be equal to 0. Directly gives you VBC is equal to 10 pound force positive. Take moment about the end point here. Then what are we going to get? MBC is positive using equilibrium equation sign convention. VBC does not contribute. 200 pound force also leads to anti-clockwise moment. 210 times x from this point, and then we have 200. This is not 210, 200. Then we have the force 210, which is leading to clockwise rotation. So I'm going to write 210 times 4 plus x from the other end should be equal to 0. So we get an expression for MVC, bending moment. Take the terms to the other side, we get 840. We had minus 210 x, take it to the other side, plus 210x, and then minus 200x, so becomes 10x. So this is the expression we have, and we can draw the bending moment diagram. For the right end, we can get a section here. It's very easy for CD, section CD, it's very easy. Draw the free body diagram from the right end instead of the left end. Point D. We know at over here, point D, the reaction force is R2. R2 is 90 pound force. Take a section, represent the reaction forces, but this is some arbitrary distance x. What is the distance? What is the limit of this distance? X, between C and D, the total distance is 10 inches because the total length is 20. Up till the point C, it is 10. So we have 10 inches here. Okay, so your X varies between the values 0 and 10 inches. Okay. We have to denote what are the reaction forces. Since we made a cut on the left hand side, my shear force is going up, leading to clockwise rotation of the beam. And then remember, for the blue color quantities, we are using the second sign convention to fix the directions. Okay, so this is the positive direction. Now again we can write the equilibrium equations. Sum of the forces in the y direction, VCD is positive, plus 90 must be equal to 0. We get shear force, internal shear force is negative 90 pound force. Go to the other side for the moment. Take moment about the left end. VCD will disappear. We have MCD, which is negative, using the sign convention, equilibrium sign equation sign convention, the first sign convention. We get MCD is clockwise and therefore negative. This 90 pound force leads to anti-clockwise rotation, therefore it should have a positive value. 90 times x must be equal to 0, and we get the positive bending moment value equal to 90x. Remember, x starts from right end and x increases towards the left here. Okay, so we can see from the equations here what are the shear forces. We can draw the shear force and bending moment diagram. Okay, so let's see if we got the right values. In the first case, VAV, we have positive 210 pounds. That is the shear force. In the second section here, VBC, we have 10 pound force constant. That is the value we have. And in the third case, we get minus 90 pound force and therefore minus 90 value. Okay, so the shear force diagram is okay. Draw the bending moment diagram. We go back to section AV and we see 210 times x. On the left hand, x is equal to 0. MAV is at that point is 0. We put 4 here and we will get 840 pound force inch. And that is the point here corresponding to the point 4 inches. Now in the second section, we have these values right at the point B, x is equal to 0 here, and we get 840, which coincides with this 840 value. At the point C, on the other hand, x is equal to the value 6. Yes, so x is equal to 6, and we get 60. 6 times 10 is 60 plus 840 will become 900, and we have a value of 900. Okay, so last section, if you see, 90 times x is equal to 0 on the right hand, and we get 0 value. And we substitute x is equal to 10 at the point C, and we get 900, the same value. So linearly varying. So we know how to draw the shear force and bending moment diagram for this simple case. We have seen in the 2D case how to draw the shear force and bending moment diagram. What about a 3D case? You will often get problems where you will have to draw the shear force and bending moment diagrams for 3D case. So how will you draw the shear force or bending moment, shear force or bending moment diagrams for 3D case? Especially in shafts, you will be asked to draw the bending moment diagrams specifically. Okay, so how to draw in 3D case? What you have here is a shaft with 2 pulleys. One of the pulley at B has a force in Z direction, and the pulley at C has a force in the Y direction. So how do we solve it? We can split this problem using principle of superposition. What is principle of superposition? If you have 2 forces acting on a member, you can treat the problem one force at a time. So basically, I can take this shaft, consider only the force at B and neglect the force at C, and try to solve this problem separately. Then in the second problem, I will try to solve with the force on C, neglecting the force at B. Okay, and I will get another solution. If I add the solutions together, I will get the solution for the 3D problem. Okay, so that is the idea we have here. And it's very simple. We know how to obtain the bending moment diagram. So in 3D case, what I'm going to do, use the principle of superposition and split the problem into 2 different problems. The first problem I'm going to consider is on the XZ plane. So this is the x-axis and the z-axis. When I look from the top view here, what is it I'm going to look at? Will I see the forces at point C? I will not be able to see the forces when I am just looking at the 2D problem. So I can forget about the force at point C and only consider the force at point B. So let me draw the axis first by looking at it from the top. X and Z axis. So looking from the top, this is what I'm going to see. Draw the beam. This is a beam. I clipped something. Okay. We have A, B, C, and D, and 10, 10, 10 inches. Okay, so we equally divide. Okay. Okay. So at point B, I am going to see the force 200 plus 1000. Okay, 200, 1200. So that's the force I'm going to observe here. Right at point B, 1,200 pound force. Okay. I'm going to assume this is like a simply supported beam. Because of this force, I will have reaction forces here. What are the reaction forces I'm going to see at the point A and point D? I will have reaction forces. So I'm going to write RAZ since it is in the direction of RDC. I can figure out what are these reaction forces by solving it again. $1,200. Take moment about one of the points here. Let's take moment about A. What is the equation I'm going to get? Okay. So now if you use your right hand system here, right hand system, we need to be careful where the y-axis is. Y-axis is coming right out of the board. Okay. Right out of the board. So if you use the right hand system, then anti-clockwise direction is the positive direction. So we can get RDZ, and remember 10, 10, 10 inches. The distances. Based on this, RDZ times 30, and we have minus 1200 times 10 must be equal to 0. So we get the force RDZ is 1200 over 3, so 400 pound force. Okay, so this is the force we get. We can solve for RAZ. We get 800. Okay, pound force. So we have these values. To draw the shear force and bending moment diagram, we can take cuts at two sections, here and here, anywhere here in between. So sections we should consider are AB and BD. Okay, and if you do that, draw the section. At the point A, we have RAZ is 800. Pound force. And again, as usual, we need to assume the second sign convention here. Okay, so what is the positive direction? Since we are on the X Z plane going down, the second sign convention should be carefully applied here. So this is the positive X, and the Z direction is going down here, unlike XY axis, which was going up. Let's see here. So it's Z on the Z plane. in the negative direction here. So okay. Left clockwise rotation. Why it is clockwise rotation? X, Y, and okay. So here too, it will come out in the clockwise direction. So I'm going to consider A. And what is the section here? A, B. Okay. Let's see. V, A, B. And let's see here, M, A. If we consider like this, if we do we get the same values? So VAB, we get 800 pound force, take moment about this end, and we get M AB is equal to, we get the right values. So 800 times arbitrary distance X. Yes. Okay. So this is the bending moment value we get. And if you take the other section, you are going to get the same kind of values. Let's see here. This is 800 reaction. Over the other end, we have 400. We will have 400 times X in any section. And we are going to get 400 times 20, which is 800. So we need not draw the other section. We already have the bending moment diagram correctly. So we can represent the bending moment here. Now you have to be careful here. The bending moment we are calculating here is about a certain axis. What is the axis? Y. So I'm going to put Y on top of here because we are calculating bending moment about Y axis. Along the length, we have A, B, C, and D. How does the bending moment vary? Reaches a maximum value of 800, then it goes to 0 at point D. 800 here. So at point C, we can see it is half of the value, 400 pound force inch. Sorry, is it 800? No. This is 800, 8,000. Should be 8,000, right? MY 8,000, yes. Because 800 times 10,000 here and 4,000 here. So this is the result we get for bending moment with respect to y-axis. Now, for the second problem, what I'm going to do is I'm going to look at this same problem on xy axis by looking in the negative z direction. When I look at this direction, what I'm going to see is I will not be able to find this force at B. I can neglect and I can consider it as a beam with a force 600 pound force at point C. But now I have the x-axis and the y-axis, which I will see here. So when I'm looking at this direction, y-axis, x-axis. That's what I will see. Point A. Okay. And what I'm going to see downward at point C. So let's identify point B, C, and D. And right at point C, I have the force going down, 600 pound force. So I'm going to not write the units. Then we have the reaction force at point A. in the y direction. So I'm going to write it RAY. And at point D, I'm going to assume it is simply supported and RDY. So again, write the equations. RAY plus RDY equal to 600. Take moment about point A. And what is the equation we are going to get? RDY times 30, which is anticlockwise positive, minus 600 times 20 must be equal to 0. Again, we get the reaction force RDY is 30, so we will have 20 times 2400 pound force. Okay. Then we have RAY, which we can calculate as 200 pound force from the equations. So once we have the reaction forces, we can calculate the bending moment. So let's make a cut. In section AC, one cut. In section CD, one cut. That's it. Draw the free body diagram in one of the sections. The force right at the point A, we already know 200 pound force. And then we make a cut at an arbitrary distance x. We know the total x values vary from 0 to 20 inches. The internal reaction forces are clockwise here, V, AC, and M, AC. Okay. Find the reaction forces. VAC should be equal to 200. Take moment about the right end. MBC must be equal to 200 times x. That's it. At the point C, and remember that this particular moment is about z-axis, so we write it with the z in the superscript. Right at the point C, x value is 20, so we get 8,000. 200 times 20 will get 4,000. Sorry, so we are going to get 4,000. So we can draw the bending moment diagram along the length of the beam. Let's note down the points A, B, C, and D. Right at the point C, it is maximum. The value is 4,000 and goes back to 0 at point D, simply supported. At the point B, we will have 2,000 pound force inches. The units. Okay, so now this is MZ, the moment about z-axis. Now how do we add these quantities? We want to find, in most of the problems, we want to find where the bending moment is maximum. Okay. Here and here. How do we add these quantities? Because the bending moment is about two different axes. How do we deal with that? We need to be slightly careful here. Okay. The cross section of the beam can be rectangular cross section like this or a circular cross section. Depending upon what kind of cross section we have, we need to deal with these cross section differently for calculation of stresses. We will see how to calculate the stresses exactly for rectangular cross section, circular cross section, or elliptical cross section, etc. But right at this stage, how do I find what is the resultant bending moment at each of the points? Since at A and D the bending moment values are 0, both My and Mz values are 0, I do not worry about A and Z. What I need to find is at the points B and C, what are the resultant bending moment values? Now bending moment here is a vector value here. It's like a vector. You have three components: mx component, my component, mz component. What we have found is mx is non-existent, 0. Y and mz values are given at point B and C. So I can write what is the bending moment vector at point B. Mx is 0. Go up and check at point B. What is the my value? 8,000. So we write it 8,000 here. And at the point B, mz value is 2,000. So let me write it as 2,000. Similarly, I can write what is the bending moment vector at point C. 0 mx value. My value at point C is 4,000. And come down and see at mz value is also 4,000. My is 4,000, mz is also 4,000 at point C. Which one is maximum? We need to find the magnitude to find where the bending moment is maximum. How do I find the magnitude? You square and add the components, right? So that's it here. So we have 0 square plus 8,000 square plus 2,000 square. So we can use a calculator to figure it out. Square, close the brackets, take square root. So we get the value 8246.21. Okay, so this is the bending moment value, resultant bending moment value. But bending moment we know is according to certain axis. It could be x-axis, y-axis, z-axis, or in a certain direction. We can find the direction of the axis with respect to a certain axis. Okay, so for example, this is with respect to y and z. On the yz plane, if you draw, this is the y-axis, and let's see here. We are looking from the. Okay, so let's redraw this. If I look at the 3D direction. 3D direction here, and let us say I'm looking at this direction. I will see the y-axis on the top, z going on the left. So I'm going to draw in the same way. just to make sense of the direction. Y and the z-axis. So we have a component of bending moment with respect to y-axis and z-axis, but I want the resultant direction. How do I get it? It's very simple. We have along the y direction 8,000. So I can draw the component along the y direction as 8,000. And along the z direction as 2,000. Little shorter. And my resultant direction is going to be the green one here. Okay, that is going to be my resultant direction of the axis, and my bending moment is with respect to that particular axis. I at the point B with the magnitude here. Okay, now how do I find this direction? With respect to z-axis, I can calculate the angle theta. What is the angle theta? It's very simple. Tan theta is equal to 8,000 over 2,000. That get is equal to 4. And I can calculate theta as tan inverse 4. So let's cancel. And 4 tan inverse. So where is the trigonometric function? We have here sine cos tan. I want the inverse. How do I get the inverse? What is this?
Just do it equal to 75.96.
What do you get?
75.96.
7. Okay, so I don't want. I want in degrees here. Trigonometry.
Click on
Let's see.
second.
Okay. Tan inverse. Yeah. Click on second. So I think I have to write 4 here before. Let me cancel that because it's giving me some. Okay, so 0 here, 4, and then trigonometric second and tan inverse. So I get 75.96 degrees. If you leave it in radians, it will become different value, 75.96 degrees. So this is the direction, and it is with respect to this axis we are applying the moment. Now use the right hand rule and you will see the direction of the moment. Okay, if you use the right hand rule, according to this direction, my moment is the 4 fingers are pointing in the red direction. This is how I apply the moment in this direction for the point B. We can do the same for point C. Find the resultant and find the directions, and point C you will have different magnitude value, 2 times 4,000 root 2. That is the answer you are going to get. So let's see here. 1,000 times 2 square root is equal to, I get 5656. So this is lesser value. Clearly we can see the magnitude of MC is less. (4,000 square plus 4,000 square) gives me the value 5656.85. 85 pound force inches. So this is less value. And in similar way, we can also figure out what is the theta value. Theta value is obviously tan inverse 1 because 4000 and 4000 are equal. Let me cancel here. Put a value 1.
45.
45. Yes, of course. It become 45. And theta here, 45 degrees. And remember again, we have y and z values. And with respect to z-axis. Or it could be y-axis. It doesn't matter. So it is 45 degrees in that direction. Okay. Now, sometimes we will use the resultant value of the magnitude to calculate the stresses, and sometimes we cannot use the resultant value, but we'll have to use the individual values of the bending moments to calculate the stresses. That will depend upon what kind of cross section we have on the particular beam. Now let us suppose if it has a circular cross section. You are going to later find that here in circular cross section, we are going to use the resultant magnitudes. B, for example, it is maximum, right? So it reaches the maximum value. We are going to use the resultant magnitude and calculate the stress. If you recall from your solid mechanics course, what is the formula for sigma from bending moment? M over I times the maximum value. Let's say the radius is C. I will write it as C. So this way we will find for the circular cross section what is the stress. It's very simple here. Why? Because if you take the resultant bending moment with respect to this particular axis, whatever this axis is, y and z. So this is y, this is z, assuming that. Okay. The resultant direction, okay, the resultant direction of the axis will give me the direction of the neutral axis and the cross section. So let's say here, we go here, draw in the blue color. This resultant direction is the neutral axis. And the neutral axis, even with respect to the neutral axis, a circle is always a circle. With respect to y, z or neutral axis, it's still a circle. Okay. So my I value will not change in case of circular cross section. Whatever direction I go, my I will have the same formula. It does not change. So I can use the resultant bending moment value to calculate the stress here. Now let's go for a rectangular cross section and try the same thing. If I have this rectangular cross section and then I have the y and the z axis, you are going to see the trouble. My resultant axis at the point B is in some direction. What is the direction? It's some random direction here in the green color. If I use my formula for sigma, what is the formula for sigma? It's the same formula, m over I times c. If I use this formula by using the resultant magnitude along this direction, I have a problem in calculating I. With respect to the neutral axis, what is the I value for a rectangular cross? For a circular cross section, I is same. I will use the formula pi over 64 d power 4. And it is the same formula in whatever direction. But for rectangular cross section, what is it? If this dimension is b, the vertical dimension is d. With respect to z axis, I can calculate b d cube over 12. With respect to y axis, db cube over 12. But what with respect to the green axis? What is the moment of inertia? So it becomes very difficult. So what do I do here? The neutral axis, to calculate stress about the neutral axis, it is extremely tough. For rectangular section, we have to integrate and figure it out. Rather, what I'm going to do, I'm going to write my sigma differently, formula here. Sigma can be written, I can split it with respect to y and z axis. My, moment about y axis, I calculated with respect to y axis, and then I multiply, since it is with respect to y axis, I multiply it by b over 2 plus another term m z over I z times d over 2. So this is the formula I'm going to use in the case of rectangular cross section. But there is an issue with respect to y axis. We have a direction of the bending moment positive. So let me note down the directions and then you will see the problem. What is the problem? Let's use the red color for the direction. Since it is positive, my bending moment is like this, y-axis. With respect to z-axis is also positive, so my bending moment is like this. Okay. Take the y-axis, bending moment like this. Now consider the point. I'm going to name these points. Okay. This point as P, this point as Q, this point as R, this point as S. Consider the points P and S. Take the bending moment with respect to y-axis. What happens? With respect to y-axis, let me use a different color for these cases, sorry. With respect to z-axis, I'm going to use a blue color so that the signs are different. You will see that. Okay. So with respect to y-axis, the bending moment is acting in this direction. That means P and S will be under tension, Q and R will be under compression. So I'm going to put signs corresponding to that. Plus, plus, Q is minus, R is minus. Okay. Now let us take the blue moment. So let me write down the moments as well. This is my with respect to y-axis. The other guy is with respect to z-axis. Okay. The bending moment z, what does it do? It gives you tensile stresses at the points S and R. So I'm going to put plus here. Yes, and plus here. S and R plus. But if you go to points P and Q, it gives you compressive stress there. So I'm going to put a minus here. Now you see the problem. There is another problem. Depending upon which quarter I am, and this quarter, this quarter, this quarter, this quarter, depending upon it, my values here could be plus or minus, and this means it is not always additive. Okay, so we need to carefully write what is the formula. So it could be plus minus here, and it could be plus minus here also. Depending upon the point I choose, I will have plus or minus values carefully. Okay, so the stress values here, sigma, let us say I choose the point P. In that case, I will write, okay, remember, we are calculating all these stress values at the point B along the length. At the point B along the length of the beam, we are calculating the stress. But right at the point B, there is a cross section. And on the cross section, we have these different points. Okay, so at point P on the cross section, if I calculate, what am I going to get? The blue one is negative, which means my is negative. But the red one is positive, that is the mz. Okay, let's see. I think I confused between the two again. Sorry. Okay, so the my value is actually positive. So I put the positive value. And then the blue one, which is the mz value, is negative. To D2. Okay. Now, if I choose point C, sorry, point G or Q. This is point Q. Okay. So let's go to point Q. Go here. Okay, go select the red one. Red one is my, and red is negative, and both are negative, in fact. So write my over iy p over 2, and the blue one is also negative. Okay, so depending upon the point I choose, I will get positive or negative values on the cross section. And this is, again, we are using superposition principle here. We are solving and getting the stress only for bending moment in y direction, and then stresses only for bending moment in z direction, and then adding them or subtracting them using the principle of superposition. So in 3D problems, we need to be little careful. Okay, so depending upon the cross section, the stresses are evaluated differently. If it is a circular cross section, very good. But if it is an elliptical cross section or a rectangular cross section, then we need to be very careful. Rectangular square cross sections, we need to be very careful in calculating the stresses and how we use the bending moments. Any doubt here with respect to 3D problem? I'm going to stop right here, and we will continue from next class on Thursday. Okay, any doubt with respect to this problem here? Are you guys listening?
Yes, doctor. Clear.
Yes, clear.
It is clear, right? So 3D problem, be little bit careful. Next class we will see singularity functions. Now, why do I need to make cuts in each section if I have 10 different forces? I don't need to use cuts and solve the problem by taking cuts, several sections here. Rather, next class we are going to see singularity functions using Macaulay's method. We will be able to get a single equation for all the sections put together, either bending moment, for bending moment, we will get one equation, and in the case of shear force, we will get just one equation for all the sections put together. Okay. All right. So I'm going to stop right here, and we will continue next class. See you guys. I will meet you again next class.